Okay. Assalamu alaikum. Now. Okay. Okay. So now, forget about fluid right now. Come back to the heat and mass transfer, where we are not studying heat and mass transfer in this chapter. Okay. So we started chapter number 12 last class, and in this chapter what we are doing is we are just studying the radiation properties and processes, not the heat transfer related to it, but radiation itself, how does it behave, okay, and how does it get absorbed, and the related properties with it, okay. So we are studying the radiation processes and the properties. Just to give you a small recap, what we did last time is that we studied the black body, and the definition of the black body. It has three components, very important. I told you that memorize those three components. That what is a black body? A black body is a body which is a perfect emitter. So it emits radiation, and so perfect that no other body in the world can emit as much as it can. And it is a perfect absorber, and when it absorbs radiation, so much perfectly it absorbs all the radiation that nobody can absorb as much as it can. That's an idealized body, okay, black body. And the third is that it is a diffuse emitter. Diffuse emitter means when it emits, it does not emit in a single direction. It emits in all directions in the same quantity. So that's the definition of a black body. And whenever we analyze any body, we analyze based upon the black body. So as we discussed, that every body in the world, if it has a certain temperature, if it has certain absolute temperature, whether -20, -30, -100, -200 degrees centigrade, if it has an absolute Kelvin temperature, it will emit radiation. But how would we rate the emission? How would we say that how much or how good the body is emitting? We analyze based upon the black body. Okay, so how much a black body would emit compared to how much this body is emitting. If this body is emitting as good as a black body, then this is a black body. But black body is not possible in this world. We can try to become as close to black body as possible, but it's not possible to generate a black body. Okay, so we discussed that the emission from a black body is equals to sigma T raised to the power 4. That's the emission from the black body. The sigma is the Stephen-Boltzmann constant, and it comes through an integration of a bigger law. We did not go through that integration. We just studied it in a very brief. Okay. So, anyways, when the radiations are emitted, radiation is a parameter of wavelength, and it is emitted for several wavelengths, for all the wavelengths it is emitted. Okay, and if we integrate the energy emitted by all the radiations, by all the wavelength from a black body, that comes out to be sigma T raised to the power 4, where T is in Kelvin. Okay, so this EB is the energy emitted by the black body. Black body is an ideal body. So energy emitted by the ideal body, it's sigma T raised to the power 4, and this is basically, this energy emitted is a function of wavelength. So if we add up all the energy emitting by all the wavelengths, so in mathematics when we have to add up, we say we integrate.
Yes.
So we integrate from 0 to infinite lambda. Lambda is the wavelength. 0 to infinite wavelength, all the wavelengths. So energy emitted by all the wavelengths, if we add them together, that's EB. Then the other thing that we studied, that we are going to continue from here onward as well, is the response to surface irradiation. First of all, what is irradiation? Irradiation is incoming radiation. So if there is any radiation falling on a surface, what's the total amount of radiation which is falling on a surface? That is known as irradiation. So it's a terminology. You just put an IR before radiation. So that becomes an irradiation, which is basically total incoming radiation. So basically what happens is that if I have a surface, Okay, and irradiation is represented by G. If I have G irradiation coming onto the surface, now there are three possibilities. The first possibility is that, let's say this is 100%. If 100% of the radiation is coming, if this is the irradiation, then there is a possibility that part of the radiation get absorbed into the surface. Surface gets a little hot. Hot, why? Because part of the radiation get absorbed. So G absorbed. But not necessarily all the radiation is absorbed. If all the radiation is absorbed, then it is a black body. Okay? If all the radiation get absorbed, then it is a black body. But in the real world, it's not necessary that all the radiation is absorbed, and there is a possibility that part of the radiation is reflected back. And that's G reflected. Okay? And there is another possibility. Suppose if the body is not opaque, suppose if it is like a glass or semi-transparent something where you can see from to the other side. That means there is a possibility that part of the radiation is transmitted through. Right? Anyways, the amount of radiation transmitted plus absorbed plus reflected, the combination of all three will be the total irradiation. You understand this concept? Yes. Okay. So G is equals to G reflected plus G absorbed plus G transmitted. Now suppose that the body is opaque. Opaque means, like for example this wall, you cannot see the other side of the wall. So if the body is opaque, one thing is very clear, there is no transmitted, no radiation transmitted, because if it can transmit, then you can see on the other side, but you cannot see on the other side because it cannot transmit. So for an opaque object, this will be 0. So for an opaque object, G will be equal to G absorbed plus G reflected. That's it, right? So for an opaque object, G transmitted will be 0. Okay, now when we define the reflection, absorption or transmission, we define it as ratios. So suppose 100% of the energy is coming, out of the 100%, 30% got reflected, 40% got absorbed, 30% got transmitted. Okay, so these percentages, we define the reflectivity, absorptivity and transmittivity in percentages or the ratio. Okay, so reflectivity ratio we represent as rho. Rho is G reflected over G total. Okay, so it's 40%, 30%, how much? G absorptivity we represent as alpha. Alpha is G absorbed over G. Transmitted we represent as tau. Tau is G transmitted over G. Is it clear? So we represent as ratios, as a percentage. Okay, so that's the response of to surface irradiation. That's what is there on this page. Okay, this is important. These information which I have written here, these all informations are important. Could ask something from it in the short questions. For example, if I ask, write down the equation for irradiation, incoming irradiation for an opaque surface. So for an opaque surface, the equation will be this, but G transmitted will be 0, right? So like this, the regular concepts that we discuss, nothing beyond that. Okay. Okay. So that's what about this in this page. Let's move ahead. Okay. So now basically there is one important point. Okay, now this is about if we have an incoming radiation onto the surface, what happened to that? If we have an incoming radiation onto the surface, the three things can happen to it. Okay, but as we discussed in the topic of radiation, that any object is doing two things at the same time. While it is absorbing any radiation or any incoming radiation, it is also emitting radiation. So there is no emission here. Okay? We just talked about reflectivity, absorption, transmission. Emission is a property of the material's temperature. Okay? So if I have this material, there is a possibility that some of the energy is being emitted by the material as well. Now that energy is not as a function of this. Okay? This is as a function of temperature of the body. Based upon the temperature of the body, there will be emission. We call it E. Okay? E is the emission by the body. Now the total energy which is leaving the surface of the body is known as radiosity. Now if you see here, what is the total energy which is leaving the surface of the body? We have E, which is the emission, plus we have the reflection. That's the energy which is leaving the surface of the body. So combining the two things, we call it radiosity. So radiosity is J. And if I write the equation of J, it will be what? E plus G reflection, or I can say rho G. G reflection is rho G. Okay? So radiosity is J equals to E plus rho G. Now this emission, as I told you, we compare everything with respect to the black body. Okay? So a black body is a body which is a perfect emitter. But the real bodies don't emit as much as a black body. Okay? So we define another terminology which is the emissivity. Emissivity of a body. And this is equals to energy emitted by the body, actual energy emitted by the body, divided by the energy emitted by a black body at same temperature. Because emission is a function of temperature. So emissivity is defined as energy emitted by that body divided by the energy emitted by a black body at the same temperature. If the body is emitting same amount of energy as a black body would emit, then this is a black body. Okay? So a black body is a perfect emitter, it's a perfect absorber, and it is a diffuse emitter. It emits in all directions same amount. It's clear? So we define this term. Emissivity is equals to E upon EB. So how many ratios? Emissivity is also a ratio. It's a ratio of two energies. Okay. So how many ratios we defined here? We defined here emissivity, absorptivity, transmissivity, and reflectivity. So epsilon, alpha, rho, tau. Okay. So epsilon is equals to E upon EB, okay? But this E, amount of energy emitted, or you can say E is basically will be what? E will be epsilon into EB, right? Okay, E is equals to epsilon into EB. So instead of writing this E, I can write here epsilon EB. EB would cancel. But it's not like that. I would like to write it as E epsilon and EB as a function of lambda. Because the EB or emissivity might vary with wavelengths. Okay? You know greenhouse effect. What happened in the greenhouse effect? You have, or have you ever seen a greenhouse? What is a greenhouse? Huh? That's
the supply energy from microsources?
No, for plants.
for the plants, yes. Why do they make greenhouse?
Trace heat.
Because the reason is that plant needs heat and they need to store heat. The radiations which are coming from the sun, they are small wavelength. So they put a glass. Glass has a property, it allows transmitting radiation. Small wavelength radiation can transmit through it, but larger wavelength radiation cannot transmit back. So the thing is that the radiation emitted, or the wavelength of the radiation, depends upon the temperature of the material from which it is emitting. Since sun is at very high temperature, so the radiation emitted by the sun is a very small wavelength. Okay, but when that wavelength, or when the light passes through the glass, it enter into the glass house where your plant and leaves are. It get absorbed into the plant and leaves, okay? And then the plant and leaf also emit radiation. But plant and leaf are not at that temperature as the temperature of the sun. They are at a very low temperature. So the radiation emitted by them are of higher wavelength. The higher wavelength cannot cross through the glass.
So it comes again.
So it is trapped. So the energy gets trapped in the greenhouse, and plants need high temperature to grow. Okay, so that's why we call it greenhouse effect. You might have heard about environmental pollution, greenhouse effect, because the carbon dioxide layer in the earth on the earth hemisphere, it behaves as a glass layer. It allows the sun energy to go in, but when the earth got heat up and earth emit radiation, it does not allow that radiation to go out. So the overall temperature of the earth increase. That's global warming. It has huge effects. It has because of that global warming, our ice are melting and the level of ocean is increasing, and there's so many climatic changes which are occurring because of that. All because we are not allowing the radiations emitted by the earth to go out. And how we are doing this? We are burning a lot of fuel, a lot of carbon dioxide is emitted, and the carbon dioxide forms a layer at the hemisphere at a very large altitude. Okay, and that layer behaves as a glass layer. So it's the same greenhouse effect which is being created on the earth, causing the overall rise in temperature of the earth, which has huge climatic effects. Okay, so that's the greenhouse effect. So anyways, now the thing is that everything is emitting anything that has temperature is emitting radiation, but not all the radiation is visible to us. Our eyes are sensitive to a specific range of radiation, and that is from 0.4 to 0.7 micrometer. 0.4 to 0.7 micrometer. Any radiation whose wavelength is not between this range, we cannot see it. Above or below. Okay. On all the colors, with GR, the colors within this spectrum, all the colors lies within this spectrum from 0.4 to 0.7. Okay, violet, indigo, blue, yellow, green, orange, red. These are the colors of the rainbow. Okay, so all those colors lies within this spectrum. So on one end of this spectrum we have red. So beyond that red, it's infrared. On other end of the spectrum, it is violet. Beyond that, it is ultraviolet. We cannot see infrared, we cannot see ultraviolet. What we can see is between violet to red, whatever the colors we have. Okay, so the wall here, the ceiling here, my hand, everything, you guys, we are all emitting radiations. But our emission cannot be seen by our eyes. We cannot see our own emissions, because these emissions fall in the infrared region, the wavelength emitted by us, because our temperature is not that much high. So the wavelength emitted by us falls in the infrared region. Our eyes are not sensitive to infrared, so we cannot see those emissions. Okay, so but the question is that if I close the lights here, I cannot see anything. So that's the proof. If I close the lights here and everything, so we cannot see anything. But if I open the window, then the sunlight will come and then I can see. So what is the reason I can see you guys? So it's basically the reflection of the sunlight. So sunlight comes, falls on all of you, on me, okay, and it gets reflected. Now, the sunlight has all the wavelengths. Okay, but part of the wavelengths get absorbed in my body and the remaining part get reflected. So those wavelengths which are reflected are the ones which fall into our eyes and we can see the color. Okay, so for example, his shirt is red color. So when the sunlight comes and falls on his shirt, okay, so all other colors get absorbed, only the red color pigment is not absorbed, is reflected, goes into my eyes, and I can see the red color. So that's the appearance of the color. Okay, so every body has certain pigments which can absorb certain type of wavelength and cannot absorb the other type of wavelength. And through that, we can see different colors. And through that, we have different combination of colors. So it is interesting to note that the surface absorption and reflection are responsible for our perception of color. Unless the surface is at a high temperature such that it is incandescent, emitting light as a result of being heated, color is in no way due to emission. So whatever the colors I see from you guys is not because of the energy emitted by you. It's because of the reflection, okay? Which is concentrated in the energy emitted by you is concentrated in the infrared region, okay? And is hence imperceptible to the eye. I cannot perceive that infrared color, okay? Color is instead due to the selective reflection and absorption of the visible portion of the irradiation that is incident from the sun or an artificial source of light. So any artificial source of light or the sun, they are emitting the wavelengths from 0.4 to 0.7 range, okay? And that is the thing which is visible. Now, if all the color is reflected, for example, the paper is reflecting all the wavelengths. It's not absorbing any of the wavelength. That's why it is appearing to us as white. Okay? So, for example, the bag here. The bag is appearing black. Because it is absorbing all the wavelengths. If all the wavelengths are absorbed and nothing is reflected, then it appears black.
So nothing is reflected here?
It is not perfectly black. It's grayish something. There is some reflection. But from this, we define different colors. So a leaf of the green appears green because it has the pigments that absorb all other wavelengths other than the green. So green is reflected back, so when it comes to our eyes, it appears as green. So this means what? The world is colorless. What we are seeing is the colors within the light coming from the sun.
Reflection.
It's a reflection. Otherwise, the world is colorless. Anyways, this is
How can it be color?
if there was no light or the energy emitting from you, okay, that's colorless. It's only because the pigment that you have, it absorbs some of the portion of the light and reflects the other. So the one which is reflected represents the color which is reflected. Okay? If all of it is reflected, then it becomes white. If none of them is reflected, it becomes black. Okay? So that's why sometimes the same ocean, if you see ocean, sometimes the ocean, if you see it from far, it looks like greenish. Sometimes it looks like bluish. Okay? So why the color of the ocean is changing? It's not the color of the ocean, it's the reflection. Yes?
The depth of the sea?
Yeah, depth of the sea matters.
Because the light can...
Because of the transmissivity of the light. Anyways, so as a shirt is red because it contains a pigment that preferentially absorbs the blue, green, and yellow components of the incident light. Hence, the relative contribution to these components of the reflected light which is seen is diminished and the red component is dominant. So this is red because all others are absorbed. The only one which is dominant being reflected out is the red. Okay. Similarly, a leaf is green because its cells contains chlorophyll, a pigment that shows a strong absorption in the blue and the red and preferential reflection in the green. So it absorbs the other and green is reflected. A surface appears black if it absorbs all incident visible radiation, and it is white if it reflects this radiation. We've spent 10 minutes on this slide, right?
But fun.
Fun facts.
Yes.
Okay, but we spent 10 minutes, huh? It won't be that much fun if it comes in the exam. Okay, so anyways, so you got the concept? Let's move ahead. Absorptivity of an opaque material is so much material written on it. Anyways, nothing is important in that sense. These formulas are important. Okay. So absorptivity, as we told you, as I told you, absorptivity is alpha, is the ratio of amount of energy absorbed by the total irradiation. Okay, and since this is alpha equals to G absorb over G, so I can write G absorb as alpha into G. right? And or instead of putting alpha into G, so here it is alpha is equals to, where G is what? G, total G is integral 0 to infinity G lambda d lambda. G for all the wavelength integration of all. So that's the total G, right? So alpha is equals to G absorb over G. I can write it as alpha is equals to integral 0 to infinity alpha lambda G lambda d lambda divided by integral 0 to infinity G lambda d lambda. Okay? So why I started this topic? Because as I told you, this is the same case for all the material. Like for example, I told you for the glass, a glass for certain wavelength it will allow transmittivity. For other wavelength it will not allow transmittivity. Okay? So it depends, it is wavelength dependent. Absorptivity, emissivity, transmittivity, reflectivity, these are all wavelength dependent. At certain wavelengths they will do it, at other wavelengths they won't do it. They won't allow it. You have some certain glasses where you can see from in to out but cannot see from out to in. Right? So that's all because of you play in the transmissivity. Okay, it allows certain reflections, it allows certain passage, it do not allow other passage. Okay, so that's why I have to write it in terms of the integral sign or integration of all the wavelengths. Okay, because it has variation with different wavelength. Anyways, you understand this formula, right? You understand in the same way this formula. You understand in the same way this formula. Transmissivity, reflectivity, absorptivity, same formulas, but they are dependent upon G irradiation. Okay. In case of emissivity, it is a function of emission, E. Okay. So these four formulas are of similar type. Just emissivity uses E and alpha uses G. Okay. Now here it's an interesting concept. Look, if I close the door here, windows are closed. Now this is a closed room, okay? And let's say this is my body, okay? So let's say in this room there is nothing but this body. So what do you think? The body will have certain temperature, so it is going to emit radiation, right?
Yes.
And the walls have certain temperature, walls, ceiling, floor, they have certain temperature, so they will also emit radiation, okay? So let's talk about with reference to this body. What is the amount of energy emitted by the body? It's based upon the temperature of the body, right? Based upon the temperature and emissivity, that will be the amount of energy emitted by the body. Okay? Makes sense. What about the amount of energy which is incoming radiation on the body?
Based on the temperature of the surrounding.
So that's based upon the temperature of the surrounding walls and the ceiling. So basically the emission of the walls, floor, ceiling is equal to the incoming radiation for this body. So E for this surrounding is equals to G for this. Is it clear?
Yes.
E for the surrounding, because the surrounding has walls, ceiling, floor. They have certain temperature and they are emitting radiation. So E for that is basically equal to the G for it, because all of it has where it goes. It's an enclosed surface. It's an enclosed area. So all the radiations will eventually come to it. Okay? So this is how we will replace the G's here with E. So the incoming radiation for any surface will be the emissivity of its surrounding. You get it? Incoming radiation for any surface or for any object will be the emission from its surrounding. So that's how we will replace G's with E. Is it clear? But then this E will be from the surrounding. Is this concept clear so far or not?
Yes.
Good. Don't focus and worry about the things written here. Just focus upon what I speak. Okay? These things are written in very professional or very researcher type way, okay, in the hemispherical terms.
Because it's not your slides. You know whose slides.
Okay. Okay. So, anyways, so we have. Let's leave this. Okay. Yeah. One more thing. A black body is a diffuse emitter. That means when it emits radiation, it emits radiation equally in all directions. But what do you think about a mirror? A mirror is not a diffuse emitter. A mirror is a specular emitter. What is a specular emitter? A specular emitter is an opposite of diffuse emitter. When it emits, it does not emit the same in all direction. It emits only in one direction. Similarly, when it reflects, it does not reflect in all direction. Okay, it reflects only in one direction. So in case of the mirror is basically not a diffuse body. It's not a diffuse emitter. It's a specular emitter. So specular means based upon the angle of incidence will be the angle of reflection. But diffuse mean it does not matter what is the angle of incidence. So ray coming on the surface from here, doesn't matter. Because when it's going to be reflected or emitted, it will be reflected and emitted in all directions, equal amount. Is okay? So this is a mirror. Okay? And this is a black body thing. Okay? Okay. You know this equation. This equation is very important. Based on this equation, we can come up to this equation. That's alpha rho plus alpha plus tau, it's not plus 1, equals to 1.
Equals 1.
Equals 1. How it comes? If I substitute here, G reflectivity is what? Rho G. G absorptivity is what? Rho alpha. Sorry, alpha G. G transmissivity will be what? Tau G. So cancel G. All divided by equals. So it will be what? So it will be rho plus alpha plus tau is equals to 1. That's an important relation. Is this clear?
Okay.
Okay. So let's come over to a numerical problem.
Finally.
First of all, so far whatever we have discussed, all the concepts are crystal clear to you. You do understand everything. Don't worry about what is there in the slides.
Sir, I have a question.
Yes.
Who cannot see the color as it is? What is the situation?
No, that's a different issue. For him, because when the light is reflected or any specific wavelength is reflected from the surface of the body, okay, the specific wavelength for the color for that wavelength goes into our eyes. Then in our eyes we have the receptor, which can accept and make a picture in our brain. Okay, so the problem with that guy is not in his brain, in his eye. He does not have that specific receptor which can see that color. Okay, so it's the problem there. Okay. Anyways, nice question.
Thank you.
Okay, so let's move over to a numerical. A cover glass on the flat plate solar collector. You have seen flat plate solar collectors. So flat plate solar collector has a glass cover at the top. Okay, has a low iron content, and its spectral transmissivity. Spectral means anything varying with wavelength. And its spectral transmissivity may be approximated by the following distribution. So if the wavelength is between 0 to 0.3 microns, then transmissivity is 0. So it only allows, so it's a glass and it will allow the wavelength to pass through, but only allows the wavelength between 0.3 to 2.5 microns to pass through. If the wavelength is less than 0.3, it will not pass through the glass. Or if the wavelength is more than 2.5, it will not pass. And the transmissivity is also not full. It's not like all the amount of energy coming is transmitted. It is 0.9. Okay. So 90% of the energy coming will be transmitted if it is between these wavelengths. Okay. What is the total transmissivity of the glass cover to the solar radiation? Okay. So we need to find out what is the total transmissivity. So we need to find out total tau. We know tau as a function of wavelength. We know tau as a function of wavelength, but we need to find out total tau for this glass cover. So tau is basically what? The same formula. Tau is equals to integral 0 to infinity tau as a function of lambda, g lambda, d lambda upon integral 0 to infinity g lambda d lambda, right? Now what do you think? We are talking about flat plate solar collector. What do you think will be the incoming radiation? Where is the radiation coming from? Sun, right? And sun temperature is fixed. We know what is the sun temperature. 5800 Kelvin. That's the sun temperature. Okay. So transmissivity is so the total transmissivity is this, okay, and this is the incoming radiation. But incoming radiation, we know it is coming from sun. So basically, the emission of the sun will be this. Is clear? So I can say that I will replace this with, instead of G, I will put here E. Emission, but that emission is from the sun.
Is the
Emission, right? And sun, assume it as a black body. Assume the sun is a black body. Because sun is a black body, it's a perfect emitter. Okay, it emits everything. Okay, so E, right? This thing, 0 to infinity E lambda d lambda, this is basically sigma t power 4. Okay?
yes.
Sigma t power 4, you can say this is basically EB. Okay? So let me write it here as EB. Okay? Or keep it as it is, no problem. Because the fraction here is written like this, okay? So fraction from 0 to lambda is basically what? 0 to lambda, EB lambda d lambda over 0 to infinity, EB lambda d lambda. This is we studied last time, okay? Finding out the fractions. So E lambda d lambda, okay? Now, this is integration of transmissivity, and we know as the wavelength changes how it is, how the transmissivity is changing. So let's do this integration by parts. So that means we know from 0 to 0.3 transmissivity is 0, then 0.3 to 2.5 transmissivity is 0.9, then from 2.5 to infinity transmissivity is again 0. So let me write it here as it is, okay? Instead of putting 0 to infinity, I will say first 0 to 0.3. 0 to 0.3 tau lambda, okay, E lambda d lambda plus 0.3 to 2.5 tau lambda E lambda d lambda plus 2.5 to infinity, okay, tau lambda E lambda d lambda divided by integral 0 to infinity E lambda d lambda. Is it clear? What I just did is that I made it by parts. Instead of putting 0 to infinity, I put it from 0 to specific wavelength and from that to that until infinity. Is it clear now? Okay. Now here, for this portion, 0 to 0.3, tau lambda is a constant. How much it is?
0.9.
No, 0 to 0 to 0.3 is 0. right? Since it is 0, it's a constant, it will come out, but anything multiplied by 0 is 0, so this will be cancelled. Is clear? What about this one, from 2.5 to infinity? Also 0, it will cancel again. Okay? What about the middle term? This is not 0. Okay? So it will be what? Tau lambda for this thing is 0.9, constant, comes out. Integral 0, not 0, 0.3 to 2.5, E lambda, D lambda divided by integral 0 to infinity, E lambda, D lambda. Is it clear? Is this step clear or not? What is the thing that is not clear? I just split this into 3 parts. First of all, this step is clear or not?
Yes.
Then I said that, okay, this tau lambda will come out because it is constant, but this is 0. 0, so it will cancel. Here, this is also 0, so it cancel. Here it will not cancel, so it will come out and like this. Is it clear or not? Okay, so now this thing is basically fraction. This thing is basically fraction 0.3 to 2.5. Is it clear? But in the last class we studied, if we have to use the tables to determine this fraction, then we don't do it, we have to further split it. So it will not be 0.3 to 2.5, it will be 0 to 2.5 minus 0 to 0.3. So this thing is basically f0 to 2.5 minus f0 to 0.3. Now you don't remember how is it like this? Or you remember? A yes or no would be an easier thing for me. You don't remember. Let me explain it. Okay, look, this is how, let's say, the energy content is, okay, and we have fractions from, all the fractions are given from 0. So if I have 0 to lambda 1, this fraction is given, okay. If I have fraction from 0 to lambda 2, this is given. If I have fraction 0 to lambda 3, this is given, all. Okay, so if I want to know from lambda 3 to lambda 2 or lambda 2 to lambda 3, the only way is that I get from 0 to lambda 3 minus 0 to lambda 2. Is it clear? Then I will get this band. So because in the table which we are using, this is the table which we will be using, this is the table. All fractions are given from 0 to lambda. But we want a specific band. So we will get from 0 to higher value minus 0 to lower value. That will give us the band. So if I want to know from lambda 2 to lambda 3, then 0 to lambda 3 minus 0 to lambda 2 will give you lambda 2 to lambda 3. Now it's clear? So this fraction was 0.3 to 2.5, so it will be 0 to 2.5 minus 0 to 0.3. Okay? Now how to determine these fractions? Fraction 0 to 2.5. For this fraction, I need to know what is lambda t, right? So if I know the lambda t, then I will know what is this fraction, okay? So first of all, I need to know what is lambda t. Since we are talking 0 to 2.5, so I know what is lambda. Lambda is 2.5, okay? But what about t? T is, since we are talking about the emission from the sun, so T will be the temperature of the sun. Temperature of the sun is fixed, 5,800 Kelvin. So 5,800 multiplied by 2.5. Whatever the value, you will find that value here. And correspondingly, you will find the fraction. Is it clear? 2.5 multiplied by 5,800. Whatever the value, you will find that value here. If that value is not exactly, then you will interpolate. Is it clear? So you will find that value here. Corresponding to that value, you will find f. Okay? And then once you know f, so you will substitute the f value here. Then you will substitute the f value here. For here, 0 to 0.3. So 0.3 means you first need to find lambda t. So lambda is 0.3, t is 5800. So 0.3 multiplied by 5800. Whatever the value, you will find that value here, find the fraction for it.
Then subtract and multiply 0.9.
Then multiply 0.9 with it. So as if we see the solution, so look at here. It was 0 to infinity, but then by dividing into parts, they did not write in the book that this thing written and then cancelled to 0. Directly written the middle part, which is 0.3 to 2.5. 0.9 multiplied by 0.3 to 2.5, this is E upon E. Okay? So, but for that, first we need to find out what is lambda t. So lambda 1t will be 0.3 into 5800, lambda 2t will be 2.5 multiplied by 5800. So these are the lambda 1t, lambda 2t corresponding to that fractions will be this. Okay? Once you know the fractions, now you just substitute the values of the fractions, you will get what is the overall transmissivity. So that's the overall transmissivity. Okay? Overall transmissivity of the glass. We were given transmissivity as a function of wavelength. But from that we find out what is the overall transmissivity of the glass. Do you understand the problem statement and the solution procedure, everything in it? Any step which you feel that you don't understand, please ask. This chapter is such that if I ask you to go through it yourself, you can never. This is because the way it is written in the book, it's really very hard to grasp. Is it clear? Do you understand the solution, problem solution or not? Okay. Once again, is there any step that you don't understand?
No.
Okay, so let's move ahead.
Kirchhoff.
We have time. Okay, Kirchhoff's law. You studied Kirchhoff's law, right?
The sum of the voltage equals 0. The sum of the current equals 0 in the loop.
Good. That's the Kirchhoff's law in the electrical circuits, right? But Kirchhoff was the one who also worked here and in many other places. Okay, so he made a Kirchhoff's law here, and this is a very fundamental law. I mean, he put it in terms of the variables, but in reality, what he says is the nature. We all understand. Look. If I have a body which has, let me close it. Okay, if I have a body which has a fixed temperature and the temperature is not changing, what does that mean? Does the body is not emitting radiation? It is emitting radiation. Any body which has a specific temperature, it is emitting radiation. When the body is emitting radiation, it is losing energy. If it is losing energy, its temperature must drop. But if the body is at a fixed temperature, its temperature is not dropping, what does that mean?
He's getting also energy.
He's also getting energy. So the amount of energy lost by the body is equal to the amount of energy gained by the body. Amount of energy emitted by the body is equal to the amount of energy absorbed by the body. Is equal? Is it clear?
Yep.
This is Kirchhoff's law. Okay, so what he said is that, look, emission depends upon emissivity of the body. There is nothing as a black body in this world, it doesn't exist. So any body that exists in the world will have an emissivity less than 1. 1 is the emissivity of the black body. Similarly, there is nothing as a perfect absorber. No body is a black body. Okay, so if any body is absorbing energy, its absorptivity will be less than 1. Okay, but a body which has a fixed temperature means the amount of absorbed energy is equal to the same as the amount of emitted energy. In other words, its emissivity is equals to its absorptivity. Is it clear? So that's what it says. Epsilon is equals to alpha. This is Kirchhoff's law. For a constant temperature, if the temperature of the body is changing, then epsilon is not equals to alpha. It's clear? So Kirchhoff's law equates the total hemispherical emissivity of a surface to its total hemispherical absorptivity if isothermal conditions exist. So epsilon is equals to alpha. Is it clear? So this thing is important. Can ask you in the exam, what is Kirchhoff's law?
In heat and mass transfer.
In heat and mass transfer. So Kirchhoff's law means emissivity of the body is the same as the absorptivity if somebody write, okay, I'm giving you an example. If I ask in the exam what is Kirchhoff's law and somebody write epsilon equals to alpha, and he will say, oh doctor, I have written everything. Enough.
Wrong.
But I will deduct some mark. Why? Because there is a specific condition when alpha is equals to
Temperature's constant.
if the temperature of the body is constant.
And the answer will be the law and the
If the temperature is constant. For isothermal conditions, if isothermal conditions. So you forget to write if isothermal conditions, then you're gone. Okay? Okay. Okay, now there is another concept, diffuse gray surfaces. Diffuse, you know, a surface which is emitting or reflecting in all directions in equal amount, that is diffuse. Okay, but what is a gray surface? A gray surface is a specific surface in engineering. Gray surface is a surface which is independent of wavelength. Okay, so the surface has emissivity, the surface has absorptivity, the surface has transmissivity. Okay, all these parameters. But if these parameters are not a function of wavelength, that does not depend upon wavelength, then that is a gray surface. Is it clear? This is an engineering terminology for the gray surface. So look here, these two sentences, mark them as important. Diffuse because of directional independence. It does not depend upon direction, same in all directions. Gray because of wavelength independence. It does not depend upon wavelength. It's clear? Let's have another numerical. Okay. A diffuse fire brick wall of temperature 500 Kelvin has the spectral emissivity shown and is exposed to a bed of coals at 2000 Kelvin. So basically I have a brick wall and the brick wall is at 500 Kelvin. Okay, I have a brick wall, it is at 500 Kelvin. Okay, and it obviously, since it has certain temperature, so it is emitting radiation. So the emissivity is a function of wavelength here. Okay, and how it is a function of wavelength, between 0 to 1.5 emissivity is 0.1, then between 1.5 to 10 emissivity is 0.5, between 10 to infinity emissivity is 0.8. Okay, this brick wall is exposed to the coals. Okay, so the thing is that the emission from the coals is going to come and fall on the wall. Okay, determine the total hemispherical emissivity. So we need to find total emissivity and emissive power of the fire brick wall. So we need to find out the total emissivity and emissive power of the fire block of the fire brick wall. what is the total absorptivity of the wall to the irradiation resulting from the emission by the core. Okay. So we need to find out what is the total emissivity of the wall, then what is the total amount of energy emitted by the wall. Emissivity is a ratio. Okay. Then we need to find what is the total amount of energy emitted by the wall. Then what is the total amount of energy absorbed by the wall. These are the two things that we need to find out. Okay, for finding out the emissivity, so what we will do, emissivity total will be what? Emissivity of the wall. It will be integral 0 to infinity and emissivity lambda E lambda d lambda divided by integral 0 to infinity E lambda d lambda. Is it clear? Just like this. Now I will write it as integral 0 to 1.5. Okay, I will write here like this instead of writing it again and again. Okay, plus integral 1.5 to 10 plus integral 10 to infinity. Okay, divided by integral 0 to infinity E lambda d lambda. Is it clear?
Yes.
Now this thing is equals to what? So I have here 0 to 1.5, it is 0.1. 0.1 and this will be fraction 0 to 1.5 plus then the next is 0.5. Okay, and this will be fraction 1.5 to 10, then plus 0.8 and this will be fraction 10 to infinity. Is it clear?
Last exam, integration from 0 to 1, 3 was 0.
Yeah, here it is not 0 because here it is 0.1. 0 to 0.1 is 1.1. Okay. Now I will write here, since it is a fraction 1.5 to 10, I can write here as f 0 to 10 minus f 0 to 1.5, right? Since this is a bandwidth, lambda 2, lambda 3, the one which I explained before. Okay, so I can write it here as this, and this I will write here as 1 minus fraction 0 to 10. Do you understand it or not? Why? Because f 0 to infinity will be 1. Fraction, it's a fraction. 0 to infinity will be 1. Total fraction is 1, total energy. Okay. So when we say f 10 to infinity, it will be means f 0 to infinity minus f 0 to 10. 0 to infinity is 1. You don't understand that. Here. See here, these are the fractions, all from 0 to lambda. When the lambda is increasing, this fraction is increasing. When the lambda goes infinity, the maximum value of fraction will become 1. It's clear? So for f 10 to infinity means f 0 to infinity minus f 0 to 10. Okay? F 0 to infinity is 1. So that's why it's 1 minus f 0 to 10. Is it clear now or not? Okay, so here I can find this term, I can find this term, this term, this term. How will I find these fractions? I need to first find lambda t. Okay, lambdas are these lambdas. Okay, and t will be, since this is the emission from the brick wall, 500. Okay, so corresponding to lambda t, I will find the value. Corresponding to that, I will find the fraction, and then substitute these fractions in here, and we'll get what is the overall emissivity. is forgetting the overall emissivity, is there anything that you do not understand? Feel free to ask, because you are the one eventually giving the exams and you are the one eventually going to get the results. So it's not my concern. I will go. If you feel difficult, difficulty, ask.
What is the denominator?
I forgot to write the denominator. Yeah. No, I did not forget to write the denominator. This term, fraction, is this over denominator. Is clear? Fraction is this over denominator. In each one. Is it clear now?
Yes.
Is there anything else? Ask if you have questions.
That will ask.
Okay. Is it okay?
Okay.
Good. So now we find out what is the emissivity. Okay. Now we need to know the emissive power. We know that emissivity is equals to E upon EB. Emissivity is E upon EB, where E is the emissive power. This is what we need to find. Emissivity we already found. EB is sigma t to the power 4. Just so when you find out emissivity, so E will be equals to emissivity multiplied by sigma t power 4, where T is the temperature of the brick wall. So that's the emissive power of the brick wall. Okay. So let's see the problem here. You see here it's divided into 3 terms. Okay. Then find out the fractions for the 3. Substitute for finding the fractions. We have to multiply lambda by t. Okay. So multiply by t is 500 because we are using the brick. We are considering the brick wall. So we get this fraction. We get this fraction. Substitute all these fractions into this equation, you will get what is emissivity. Emissivity here is 0.61, total emissivity. Now once we know the total emissivity, then multiply total emissivity with emissive power. Epsilon multiplied by EB. EB is sigma t power 4. To find out the total emissive power. So the total energy emitted by the wall is 2162 watt per meter square. Okay. Is it? Okay. Is it clear or not?
Yeah.
Till this step, is it clear or not? Okay. Now we have the next part. The next part was, the first part was to find the hemispherical emissivity. We did it. Then emissive power of the brick wall. We did it. Now what is the total absorptivity of the wall? Now we need to find out the total absorption of the wall. Right? For finding total absorption of the wall, so that will be what? Absorption will be alpha here, and then this will be alpha here, right? And then this will be G, right? This will be G, this will be G. Is it clear? For finding out the total absorptivity of the wall to irradiation, so this will be alpha, alpha, G, G. Is it clear?
And the same procedure.
Now the thing is that, what do we have? Do we have alpha changing with lambda?
No.
We don't have that. Okay, but we have a word here, diffuse. And diffuse, whenever something is there for diffuse, that means Kirchhoff's law is applicable. And the Kirchhoff's law says that alpha is equals to epsilon.
So we can use epsilon.
So we can use epsilon. Okay. Where it is? Yeah. Okay. So since the surface is diffuse, alpha is equals to epsilon. Since the surface is diffuse, alpha is equals to epsilon. Okay. Now we can use here, instead of alpha epsilon, we can use here alpha. So consider the same graph is applicable for alpha. Now
We will get the same result.
you get the same result, but remember one thing here. You have to find G. Now G will be what? G will be the irradiation coming, right? But the irradiation coming is from the coal, which is at 2000 Kelvin. So the emissivity of the coal or emission of the coal is the irradiation for the block. Is it clear? So now I will again replace G with E, but this is for the case of coal. You will not use lambda T. T will not be 500 Kelvin. T will be 2000 Kelvin because this is the emission of the coal, which will be the irradiation for the brick wall. Is it clear? That's the concept, that if I want to know that what is the irradiation coming on this, it will be from the surrounding. So the temperature of the surrounding will be used because the emission from there will be the irradiation here. Is it clear? So here I will again use E. So now it's like solving the problem again. It's now like solving the problem again, but this time instead of using temperature 500, I will use temperature 2000. Same procedure. Is it clear? So the same procedure applied. So initially we had this. Alpha will be equals to emission for TC, temperature of the coal. Okay. So the same formulation, but instead of temperature 500, you will use 2000. Find out lambda T, then corresponding to lambda T, find out the fractions, substitute the values. You will get this as alpha. Is it clear? The only thing conceptual here was that when you are finding the emission for the brick wall, you use the temperature of the brick wall. When you want to find the absorption by the brick wall, then you have to use the emission for the coal. Emission from the surrounding is the irradiation, absorptivity of the, okay. And the thing why alpha is equals to epsilon is because of the word diffuse. If the word diffuse was not there, then alpha is not equals to epsilon. The Kirchhoff's law becomes applicable when the word diffuse is there. Okay. Is it clear? Anything which was not clear, you can ask. Okay, now let's come over to the next problem, which is the last problem for this chapter, and the chapter number 12 is done then. We did not really go into the details and the depth. We skipped many things. But if we go into the details and the depth, this chapter is the most difficult chapter of the book. Okay? Huh? Then chapter 11 or any chapter. Because the reason is that these are some very new things that you're going through. Okay? It was not like there was a continuity from chapter number 1 till chapter number 11. Now here the continuity is broken. You're studying something different, very different. Then what?
Depends on other course, I mean.
Not, yeah. For renewable energy, only a little content, not much.
Not previous course, not.
Yeah. No, it does not depend upon any previous course. Maybe physics. I don't know. Okay, so let's have this numerical, and we finish the chapter. A small solid metallic sphere has an opaque diffuse coating for which alpha is equals to 0.8. For lambda less than equals to 5 microns, and alpha is equals to 0.1 for lambda greater than 0.5, lambda greater than 5 microns. So it's like this. From 0 to 5 micron, 0.8, then from 5 to infinity, it is 0.1. And this is what? This is alpha. So absorptivity is given for the coating of this sphere, metallic sphere. The sphere, which is initially at a uniform temperature of 300 Kelvin, this sphere, metallic sphere, is initially at 300 Kelvin, is inserted into a large furnace whose walls are at 1200 Kelvin. So you put this sphere into a furnace, which is, the walls of the furnace are at 1200 Kelvin. Okay. Determine the total hemispherical absorptivity and emissivity of the coating for the initial condition and for the final condition, steady state condition. First of all, we need to find out the total hemispherical absorptivity. The absorption by the sphere is equal to the emission by the walls. Absorption by the sphere I have a sphere. This is a sphere, a ball in the furnace. Let's say this is a furnace. Walls of the furnace are at 1200 Kelvin. The ball is at 300 Kelvin. Absorption by the ball is equals to the emission by the walls of the furnace. Okay? And emission by the ball will be based upon its temperature. So it's like the same formulation, only the thing is that when we are considering the absorption, we have to consider the temperature of the walls. When we are considering the emission, we have to consider the temperature of the ball itself. Is it clear or not? Okay. So and it is diffuse. So diffuse means the same graph will be there for absorption as absorptivity will be there for emissivity. Alpha is equals to epsilon. Okay. So for alpha, this is the main formula. Alpha is equals to alpha lambda g lambda d lambda upon g lambda integral 0 to infinity alpha d lambda. Okay. But this g will be what? This g will be the E
Of the wall.
of the walls. This G irradiation on the ball will be equal to the E of the walls, emission of the walls. And the walls are at 1200 Kelvin. Okay, so this G is equals to E. TF means temperature of the furnace, at the temperature of the furnace, or temperature of the walls of the furnace, 1200 Kelvin. Okay, since it is 0 to lambda, 0 to infinity. So, and now here we have two ranges from 0 to 0 to 5, then 5 to infinity. So we'll do it in two terms. So it will be 0 to lambda 1 to infinity. Okay, and so it will be, then it's the same thing. It's a fraction, and from lambda 1 to infinity it will be 1 minus 0 to lambda 1. Okay, the same thing that we did. Since TF is 1200 Kelvin, we'll find lambda T as 6000 micrometer Kelvin. Corresponding to that, the fraction is 0.738. Substitute the values, you will get alpha is 0.62. Is it clear?
So why in the denominator he didn't write the integration for the EB?
As I
Like
told you,
like
see?
what you said.
You see, this thing, I can write this thing or I can write EB. Same thing. I can write this thing or I can write EB. No problem. I can write, similar is the case for G. I can write this thing or I can just simply write G. Is it clear? Then when we have to talk about the emissivity, for emissivity it's the same graph, but now we have to use the temperature of the ball. So temperature of the ball is 300 Kelvin. It's again from 0 to lambda 1 to infinity. Okay, and the same formulation, so you will get emissivity 0.11. So that's the initial condition. So initially the ball has an emissivity 0.11 and its absorptivity is 0.62. Makes sense. The ball is at 300 degrees centigrade, the walls is at 1200 Kelvin. Okay, so emissivity will be less, absorptivity will be more. So the temperature of the ball will rise. Okay, when the final steady state temperature will reach. Now you see here, it's written that whose walls are 1200 Kelvin. It's fixed temperature. The furnace is a very big furnace. It is of almost fixed temperature. So eventually, the furnace temperature would remain 1200, but the ball temperature would rise from 300 to 1200. And when this will happen, then the ball temperature would remain steady state. After reaching 1200 Kelvin, the ball temperature would remain steady state, and that means emissivity is equals to absorptivity for the ball. Amount of energy emitted by the ball is equals to the amount of energy absorbed by the ball. Okay, and that means the initial absorptivity was 0.6, initial emissivity is 0.11, but as the temperature of the ball keep on rising, its absorptivity will keep on rising until it also reaches 0.62. So then in the final state, emissivity will also be 0.62, absorptivity will also be 0.62, and the ball will be at the same temperature as the furnace walls. Is it clear? So that becomes the answer for your next part. And with this, the chapter is closed.